The question, is the world local or non-local? Seems to be, to many of you, just an obvious one. Hasn't it been proven by quantum mechanics that the world is non-local? We talk about non-local correlations. But of course, as the experts among you know, we are talking about local observations in quantum mechanics, which says nothing about the non-locality of the world per se. So if I talk to students, they say, oh, well, why are you even bothering to ask the question? It's all settled. But of course, this is an ontological question. This is a question about metaphysics, about how the world really is. And we're going to dig a little bit into that, separate out the issues there, and see how that question connects to the question of emergence and what motivates to even bring emergence into this picture. So I will do a general orientation and discuss why emergence. I will just go through the objectives of the symposium, and then I will just share with you, what to look for during those next 3 days. Let's start right here. The big question, of course, in physics in last decade, since the beginning, is the question of unification, all the way through the 20th century, about how to unify gravity, and quantum theory. Maybe emergence theory can be a connecting element, can be the consideration of emergence theory. Maybe can that be a way forward? Clearly, quantum theory, as we understand it today, is an entirely indeterminist theory, a non-causal theory. And below the level of the quantum, there is no real reality. We can't talk about it. We have an operational theory. It works beautifully. There is no need to assume any reality below it. We can predict the quantum correlations with very high certainty. On the other hand, general relativity, gravity, is a theory of reality. It's causal. It's deterministic. And now, you have, of course, a total contradiction of the underlying metaphysical assumptions in both these sets of theories. And this, of course, shows up already in the measurement problem all the way through. When I talk about metaphysical assumptions, I mean an assumption like determinism versus indeterminism, an assumption like non-reality versus reality. And so metaphysics, why metaphysics even in quantum physics? What has metaphysics to do with all this? Well, metaphysics is neither mystical nor irrational. What we mean by metaphysical is that a metaphysical analysis refers to the first principles, the foundational physical assumptions, which inevitably underpin any scientific analysis of nature. That's what we mean by metaphysical. Metaphysical assumptions essentially constrain the application of any mathematical theory to quantum phenomena. So you might do modeling and all that, but you're always driven by underlying assumptions about how the world is or isn't. So that's what we mean by metaphysical assumptions. So it really covers also the worldview of the scientist, how you approach the problems you're studying. And usually that's unexamined. Usually you don't look there. You just want to solve problems. But of course, how you solve problems depends on where you're coming from in terms of your worldview and your metaphysics. So maybe what happened in recent years is there's an emerging field of emergent gravity, emergent space-time, as a possibility to maybe connect to quantum theory. What does that mean, emergent gravity? I'm using this quote from David Gross. This is from a Festschrift for Jacques Aronoff on his 80th birthday, coming out in 2012, edited by Jeff Tollakson and Strupa. And he says, many of us are convinced that space is an emergent, not fundamental concept. We have many examples of interesting quantum mechanical states for which we can think of some or all of the spatial dimensions as emergent. Together with emergent space, we have the emergent dynamics of space and thus emergent gravity. But it is hard to imagine how time could be emergent. How would we formulate quantum mechanics without time as a primary concept? Were time to be emergent, our understanding of quantum mechanics would have to change. So if you go all the way with emergent space-time, emergent gravity, you have all sorts of problems coming up in interpretation and in application of the theory, and maybe that lies in our future. So maybe, just maybe, what is needed is also, once you discuss emergence at the level of space-time and gravity, that a future unification will also depend on having an emergent understanding, applying emergence theory to quantum theory. And maybe there could be a connection that way. Of course, then that would change in emergent quantum mechanics. There would be some kind of determinism there, some kind of underlying reality and see, I've quote-unquote determinism, because what we're really talking about is that you can't have predeterminism, and I will discuss what that means. So from a total contradiction of metaphysical assumptions, maybe we can go to less contradiction in the assumptions, maybe on the way to resolving the measurement problem as well. And so today we stand here on the problem of unification. We really have no good way forward, although there are many proposals out there, of course. It's a highly active field for decades. But maybe, just maybe, there is a new way to look at the problem when you look at emergence theory in the context of space-time, as well as in the context of quantum theory. So that is one motivation to do an emergent quantum mechanics. This is, of course, very futuristic, far down the road, but it's a vision that does make sense conceptually as well as metaphysically. So there might be maybe in the future an emergent quantum gravity, who knows? But what is emergent? I've been using this word all the time. And so we thought we have to say something more about it. And so what we're going to do is the following. Emergence comes up under all these different names. You've heard about complexity theory, chaos theory, self-organization theory, nonlinear dynamics, fractal sets, cellular automata, synergetics, and on and on and on. The last 20 years, you can't get away from hearing emergence in one way or other in science, as applied across all the sciences. Emergent events are characterized by sensitive dependence on initial conditions, the emergence of global order from local randomness spontaneously, and the transition of indefinite to definite states. So the way to visualize this is an emergent structure, a highly ordered structure, and due to local, randomized, microscopic interactions, interacting with boundary conditions, here signified by the circle, give rise to a global structure. So you really have order emerging from randomness. And it's just magical. I've worked in these systems, in experiments for many years, and done theory on this. So I come from this into quantum mechanics. These events are characterized, of course, they are thermodynamical events, but the most important point in this context is that they're self-referential, recursive processes, and that makes them computationally non-reducible processes. What that means is then you end up with unpredictability of individual events in these systems. Because of the intrinsic self-referentiality of these systems, it would require, in some cases, infinite amount of computational resources to predict individual events. So you can't, it's impossible. That is what is meant by in-principle unpredictability. So that's what we call, and we just invented the slogan, this is what we mean by determinism without predeterminism. So you still can have realist theories, but that doesn't mean because you have a realist theory that you have predefinition of values, pre-existing values, or predetermined values. These values actually are established in the measurement process itself, from an indefinite to a definite state. So, of course, any kind of emergent quantum theory must respect the following. Quantum mechanics is incompatible, clearly, with the proposition that measurement outcomes have predetermined values, independent of measurement. And emergent quantum mechanics agrees on this with orthodox quantum mechanics. In EmQM, measurement in emergent process describes transition of indefinite states, they might be ontic, into definite states. That's the basic background assumption here. What is emergence? In nature, this is a spiral dynamics, for example. They exist at hundreds of light years, 1,000 kilometers across, millimeters in Belousov-Zhabotinsky reactions, for example, here, in other systems. So they're scale-free. You have emergent property. There is no spiral code here. The spiral dynamics is an order that emerges from random interactions entirely. There is no spiral code there anywhere. So this is the global level. This is what you can see. Underneath, you have only local randomized interactions. And so, for example, these long-range correlations, they're entirely unpredictable locally on the level of individual events, and yet they're completely deterministic. So here you have, so what happens at this boundary from microscopic to macroscopic? And the questions that arise here are very similar to what you find in the traditional quantum measurement problem. How do you go from microscopic to macroscopic states? What happens there? So there is 3 different ways to think in terms of causality on what happens here. I just want to review. There's bottom-up causality. So you might say, well, it's all set up in the local interactions. That gives rise to an emergent structure. And this is what is called weak emergence or epistemic emergence. This is also called theory emergence. And this goes under the term supervenience. Supervenience describes global properties or structures based on entirely local processes that can be reductionistically described, but the properties themselves supervene on that. That's weak emergence. Then you have top-down causality. The problem, of course, with top-down causality is where should that cause come from? Out of nothing? From the top? Oh, sorry. Of course, that's a scientifically untenable assumption. Causes must have reasons. They come from somewhere. So top-down causality doesn't work when it's not part of emergence. What is emergence is the combination of bottom-up causality with top-down causality, and it can be called relational causality. Both arrows, both directions interact, and that gives rise to a continuum description of the process. And that's called strong or ontic emergence or physical emergence, and that's the kind of emergence Gerhard was talking about in his introduction as well. And that's what many people are looking at when you look at emergent gravity, for example, or emergent quantum mechanics. Of course, the big question here is what's the relationship between the information level and observations at that level and causality? And it gets even more stranger when you look at nested hierarchies of emergent states that connect different levels, because one level here, one element of the lower level can be itself an emergent structure at another level, and so on. And this is known as a scale-free relational continuum. And this is known as the fractal universe concept. That's fractality all the way through. So you have scale-free notions, you have intrinsic self-reference, and so on. So this is an entirely new worldview that we're just beginning to apply to quantum theory and see where it leads us. Recently, a brand new book discussed it, the emerging quantum. And we have Anna Maria Chetto here. He's going to speak this afternoon, probably on this book and the results of your research. It's one way to approach a quantum structure as an emergent structure, based on basic Nelson's stochastics theory as well. Play a big part in that, I think. But of course, there you always have the problem, could there be a subquantum medium? You know, where do these interactions arise from? Because there's nothing but the quantum. So it's quite an exotic assumption, but who knows? At the center, though, is a new concept of causality. And we've, in recent years, seen a renewed interest in causal questions in quantum mechanics. And there's many different ways. So are we discovering a new kind of causality? The non-local causality concept introduced by Bowie, highly discussed by Bell as well, or Maudlin recently. There's time-symmetric causality. With retrocausality, there is relational causality concept, but there's also a quantum causality concept defined by Charles Bruckner, for example, indefinite causal order. And I just quote from his beautiful paper in Nature Physics on this. We've only begun to scratch the surface of quantum causality. The deeper we dig, the more questions arise. Of course, these are all seemingly incompatible concepts right now. But causal structure, thinking about causal order, causal structure, is something that is happening in quantum theory again today, and that hasn't happened 20 years ago, very much. Ultimately, you know, what if causality itself is not fundamental, is a question we must face as well. So let me go from this brief introduction on emergence to just repeating the objectives of the symposium. Number one, is the world non-local or local or non-local? What is non-locality stands at the center of the meeting. Attached to this is, of course, the pivotal question. If there are really non-local influences in the world, meaning connecting points for real, not just operationally in terms of observations, why can't they be used for supernormal signaling and communication? Because otherwise, the non-signaling constraint would be violated. This brings up the role of the scientific observer and agent. How to account for observation in realistic approaches. Another big problem, the problem of free will, and so on. Also unresolved as of yet. Finally, and this is a new element in this meeting, on day 3, we're going to talk specifically about space-time and gravity in this context. We're excited about this new addition to the program. And we're going to hear about new experiments throughout this meeting. I just want to focus briefly on what is non-locality, and I just want to do this by briefly, one slide per paper, discussing I spent a lot of time with these three papers the last 2 years, as have many of you, I'm sure. And let me just start with Bell, of course. And I just want to bring up one quote by him from the last interview he has given at CERN in 1990, where he was asked, what is non-locality, Professor Bell? And he said, non-locality means that what you do here has immediate consequences in remote places. And the story goes that he pointed to his desk and then to the mountain peak. And so, he was a realist in some sense about non-locality. But of course, you can interpret him this way and that way, and you can find quotes this way and you find quotes that way. But what the exact nature is of this immediate consequence of non-locality is exactly what is under dispute since EPR, at least, 1935. This famous paper, and I don't want to bore you, you all know the conclusions, but that paper concluded that orthodox quantum theory must be incomplete because otherwise the world would have to actually be non-local. Local realism must be violated. And of course, Einstein rejected spooky action at distance, he rejected non-locality, or as Bell later said, these immediate consequences of actions here on remote places. But Einstein and Bohr, in all the debates, they agree on one thing. And you make a lot about, Einstein being a determinist and Bohr being not committed to determinism at all. But they clearly both agreed that non-local influences, real, intrinsic, objective non-locality, cannot exist. And they're in agreement about that, but for very different metaphysical reasons. But we can't get into that. But then comes along David Bohm in 1952 and publishes an alternative approach towards accounting for quantum correlations based upon this very forbidden idea of intrinsic, objective non-locality. And of course, he didn't set out to do this. He just said, this is a mathematical possibility. And of course, Einstein called it a cheap solution, a trick that can't work. But here we are. In 2015, 8 years after EPR, we call such non-local quantum theories ontological, or also now recently psiontic quantum theories. They still create interest. People still deal with the ideas that David Bohm initiated a long time ago. And so, is the world local or non-local? Well, according to psiontic realist quantum theories, the world is actually non-local because you have an ontological assumption here about non-locality. And according to Bohm's theory, the world is not intrinsically random, therefore. It only looks random, it's unpredictable, but it's fundamentally interconnected. That, of course, flies in the face of orthodox quantum theory. So, according to the textbook operational interpretation of quantum mechanics, what is non-locality? Of course, quantum theory there is a fully indeterminist theory, beautifully worked out. It's also called, known as operational quantum mechanics. People started talking about this recently. It's known as the orthodox quantum mechanical interpretation, Copenhagen. And I just want to put up these two famous quotes that everybody cites about the Copenhagen interpretation. There is no quantum world, there's only description. And it's wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature. And so what Bohr really is saying is, science is not about ontology, because we can never say anything about how reality really is. All we can do is to accurately describe reality, and that's the operational approach. And it's the safe approach, and it's the approach that gets you results and allows you to do predictions. So why should you even ask another question about reality that lies underneath? And if you ask, so this is the comment I get, when people talk about, well, but we do observe in spade-type experiments non-local correlations at a distance. And then, what are non-local correlations? You ask the operationalist. He would say non-local correlations are correlations that cannot be explained by a local realist theory. End of story. The realist would say non-local correlations are correlations that can be explained by a non-local realist theory. So what you have here is a negative definition. What you have here is a positive definition. The operational definition is always one that is the safe one that defines in negative terms. The realist defines the problem in affirmative terms. And that's the one difference. And are they complementary? Do you need both sides of the equations to make progress? Who knows? But this is what we want to explore. So this is to sum up the whole non-locality story. there's two ways of interpreting Bell's theories, including free choice in this case, vis-à-vis non-local correlations. The operationalist approach says, I'm not dealing with reality, locality is real, but there is only intrinsic randomness. I have non-causality, subjectivity, and here you have, if you think this all the way through, you end up with cubism and a subjectivity of observation. Of course, there you have the problem that this locality is a locality without causality. The realist wants to hold on, of course, to reality and says reality can't be local. To explain these correlations, in physical terms, I need to assume that reality is non-local. Of course, Einstein's spooky exit, this would be what Einstein the least wanted. So here you have determinism, causality, objectivity, ontology again. But here you have the problem that you have a causality without locality. And this is reflected in two very different worldviews, the way you approach this problem. In this worldview of the operationalist, the world is entirely local in terms of an ontology and irreducibly random. In the realist approach of a Bohm, at least, the world is non-local and deeply interconnected, therefore, and at a very fundamental level. When you deal with free choice in these situations, the operationalist has to answer the question, how could free will prevail in a world that is intrinsically random? And in the afternoon, I will talk about the connection between randomness and free will and all that problem. And many of you have spent a lot of time on this problem. The realist must answer this question. How could free will prevail in a world that is fundamentally interconnected? Because if everything is interconnected, how could free will be even possible? So here we are at the end. This is an open question. Operationalist quantum mechanics and or realist quantum mechanics? And I say and or, because we really don't know. They might be complementary or not. Maybe there's nothing to be gained from going for realist approaches. Maybe 50 years from now we say this is an aberration in the evolution of the theory. All we can do ever is to take the operational approach, but maybe not. And this maybe not is about what this conference is all about. So the objective of the EmQM15 Symposium is to invite the open exploration of the quantum state as a reality. And you've seen the literature out there. Physicists like Dieter Zeh, for example, of decoherence fame, get very nervous about discussing quantum theory without an underlying reality. I mean, he put this book out there. It's a fascinating read, profound or delusional. And he comes down on his side, he likes reality. But also popular science writers are beginning to pick up this topic and say, well, has physics gone wrong by abandoning the search for a underlying reality? So this is out there now, not only in the community, but it's out there in the science press now more and more. And I'm sure you've reflected that. But what's interesting is that the topic, what is a common denominator now between mainstream approaches and alternative approaches, is a search for a new kind of causality, understanding the role of causal order, causal events, causality itself. And let me close with a remark on David Bohm. Because there is a connection to the sponsor of this organization, to the Fetzer Institute. David Bohm was, in fact, 25 years ago, David Bohm was a science scholar in residence at the Fetzer Institute, the sponsoring organization who set up the Memorial Trust, which set up the Fetzer Franklin Fund. And here you have John Fetzer, the founder. He was almost 90 years old at this point, having dinner with David Bohm at the Fetzer Institute. And Jeff Tollakson forwarded this image to me. I don't know where he got it from, but he got it somewhere. I don't know if he was in attendance as a student at this meeting. He doesn't remember. But I think they both would be very proud that we're still discussing these ideas 25 years later in a beautiful setting here in Vienna. And so I was really glad meeting with Gerhard Grössing a few years back. We had a joint vision about this. And so here we are. But not only that, we are particularly proud to have Professor Basil Hiley here, who has, of course, been a long-time collaborator of David Bohm's. And I know this year is his 80th anniversary, and we will have a chance on Saturday when he's giving his talk in the evening to wish him well on that occasion. But we're particularly proud as well also to have Yakir Aronov giving the opening keynote lecture on this occasion. And I think David Bohm would be very proud to have longtime collaborators together in a room 25 years later to discuss issues. And I know everybody has a divergent opinion now, has made up their own mind about things. But I think it's quite significant that we can do this event. So thank you very much.